Welcome. Today we'll be talking about how we build low-latency mesh services starting with just single-node services using actors. My name is Nikita Lapkov. I'm a senior software engineer. Previously, I worked on a bunch of databases such as MongoDB, ClickHouse, and YDB. I'm a Rust enthusiast and also a dungeon master for a group of unhinged friends. Before we dive into actors, low latency, mesh, and stuff like that, let's take a step back and look at the starting point. Why do we need it in the first place? Imagine a system with lots and lots of components. Each of these components runs some kind of business logic, and all of them must run in parallel. These components have so-called data dependencies, meaning that usually components need to consume data from multiple our components and produce data to multiple our components. So you can imagine it as a computational graph in the not a very implicit way. Different components can have different processing speeds, meaning that it is entirely possible in our computation chain to have one component that processes data at the rate of 50 megabytes per second, and then another component which only does 1 megabyte per second for whatever reason. Our components also have a requirement to be sometimes geo-distributed. So it is entirely possible for a couple of components to be on the same node, but it's also entirely possible for components to be on a completely different nodes in different geographical regions. So why actors is a solution to such a problem? And it might look a bit abstract, but that's exactly the kind of problem we encountered when building our trading system. In the trading system, you have myriads of components connecting you to different exchanges, aggregating data from these exchanges, running trading robots, and others, maybe some offline reporting as well. So why all of this zoo of different business logic entities is a good fit for actors? Well, first of all, actors as a model, as you probably already know, is a bunch of single-threaded tasks exchanging messages. So it is important to note that message passing is the only synchronization primitives we will be using here, meaning that there is absolutely no shared state. There are no mutexes, no locks, not even atomic variables. The only way to share data from one task to another is to send a message. While this model might seem a bit restrictive at first, it's actually very flexible. One of the great boons it gives us is being able to easily parallelize our system. So because there is no data sharing between threads, and because all tasks are single-threaded, you can easily spawn hundreds of them. If in your app you have a single task of some kind, and it isn't able to cope with the load, you can just spawn 100 more of them and use data parallelization to split work evenly between each of the tasks. Despite being easily parallelizable, there are no data races because there is no data sharing. Of course, with some finesse and talent, you can still introduce data races even when using message passing, but it's another class of a problem, and it's significantly harder to do so than compared to the system with locks and traditional synchronization primitives. Finally, one of the great benefits, which I think is underappreciated about actors, is that all inter-thread synchronization is explicit. Every time you want to see how your system behaves, what are the synchronization points of your system, you can take a look at the history of messages which are sent through it. And every message is a point of synchronization, and you can just look through it as a browser history and see what's been going on. So actors is a great fit for us. However, Rust itself does not support actors internally, so we need to develop this support ourselves. And that is why we created elfo. Elfo is a technology that allows us to apply actor programming to Rust. So it's a Rust framework for actor programming, which obviously supports sending messages because that's the whole thing of actors. But it does so much more. For example, it allows you to dynamically route messages based on runtime information, meaning that you can, in runtime, decide which actor specifically receives certain messages, certain types of messages, and which of them don't. It also provides Erlang-like actor restarts on failures. So if you configure actor in a certain way, you can be sure that it's always running, because if it panics, elfo will automatically restart it. So elfo provided us with a very solid foundation which we used for a very long time, but this foundation was constrained to a single node. And traditionally, people use protocols like gRPC and other remote procedure calls to take their single node application and make it distributed. While it is a well-established practice, we didn't want to add another way to send messages in a system, because that's what it basically is. In elfo, all of our business logic is already using elfo's primitives to send messages around between different parts of the system. By introducing gRPC in our stack, we're basically saying that, hey, if first of all, you need to know whenever the actor receiving the message is remote or not. And second, now you need to use a completely different API with completely different guarantees to send the message to a remote actor. So while this does mean introducing additional complexity to elfo, we wanted to have a way to completely obscure from the actor whenever the message is sent to a remote receiver or not. So how did we do it? How did we make messaging distributed? There are a couple of steps to this process. Let's start from the very beginning. Let's start with structuring our connections. When elfo node starts up, it accepts a configuration file. And in this configuration file, we have addresses of all nodes in our mesh, of all nodes in the cluster. The first step for elfo is to do discovery. It tries to connect to all the nodes listed in the configuration file by first establishing a so-called control connection. So control connection is a TCP socket, which is very low traffic and mainly used for metadata. When nodes connect to each other, they first do a so-called handshake. This handshake ensures two things. First, it rules out misconfiguration, because on handshake, nodes check if there is actually elfo running on the other side or not. And then nodes decide on the common set of features which they both support. This can be encryption, this can be compression, or some other stuff. It is entirely possible for another node to not support features which our node does. So we select a minimum amount of both sides to ensure that we're speaking on the same terms. After that, the control connection is mainly used for flow control, which we'll cover in a second. The sort of rest of the load-bearing connections in our system are so-called data connections. This is still a TCP socket, but it has a different purpose. All actors inside elfo are structured into actor groups. You can think of an actor group as a way to put a bunch of actors which do similar things together. For example, you can have an actor which handles a WebSocket connection. For example, you have like a web server and a bunch of clients connect to you. Each of the actor basically owns the socket, the WebSocket of some client. Since all of these actors probably share the same code, it also makes sense to group them in runtime into an actor group. So all WebSocket actors will live in actor group A, but maybe you might have another group of actors which do some aggregation, and so on and so forth. So between each pair of actor groups which want to communicate remotely, we establish a data connection. And unlike control, data connection is actually used to send messages from actors. So let's take a look at how do we encode them. Each of the messages in the system is represented as a Rust struct. So in our Rust code base, we have a struct which has some macroses on top of it, which allows us to later encode it as an envelope. Envelope has two things. You can think of that envelope as a byte stream with a certain structure. So first of all, it has a header which stores a bunch of useful information, such as the address of an actor who sends the message, the address of an actor who receives the message, a trace ID to support certain observability features, and a bunch of other information. The most interesting part of an envelope is the message. So the message is the thing that actually encodes the contents of the Rust struct. It has three things. Two of them are names. So protocol name, you can think of it as a package name in protobuf or similar protocols. And the message name is the name of a struct. So this is basically a way to tell to the receiving node what kind of a Rust struct this message encodes. Message payload is encoded in message pack. So it is important to know that while message pack is more efficient than JSON, it is a self-describing format. Meaning that it has name fields, and if we already know what kind of Rust structure we are sending, encoding field names is wasteful. So in the future, we are thinking about supporting other formats such as postcard or maybe something else, something that is not non-self-descripting. Now that we have encoded messages, we can optionally apply message compression on top of them. So message compression is an interesting problem. It doesn't make it sense at all if you're sending messages on the same node. But when we're speaking about nodes which are geo-distributed, which we do want to support, it is best to compress messages if you are willing to sacrifice some latency for a more efficient use of bandwidth. Basically, we're trying to pack as much information as possible into the bytes we're sending all over the network. Message compression is done using LZ4 algorithm. We were considering ZSTD initially, but ZSTD while it has a better compression ratio, it also has a slightly slower compression and decompression cycles. So LZ4 is kind of this perfect spot where it provides us with enough compression ratio of starting from 2x and more, and at the same time, it is much faster than ZSTD. So the trade-off I was talking about before between the compression ratio and message latency is quite important. Ideally, we want to accumulate as much messages as possible into our buffer before compressing it, because this provides a better compression ratio because LZ4 has more data to work on. At the same time, when we are accumulating messages in this queue, we are artificially increasing their latency because they're just sitting there waiting when we could have sent them over the network. This is really unfortunate. So we have, at the moment, we have a simple heuristic where we try to accumulate messages up to a certain amount of kilobytes, and then send the batch, send the batch down the line. There might be, so this heuristic works pretty well in practice, despite its simplicity, but we might add something more adaptive in the future. So it seems like all is well. We have encoded our messages, we have compressed them, and we have sent them over the network. However, if we just run this system as is, there can be some problems such as overwhelmed actors. Recall that in the very first slide, we told that different parts of the system can work at very different speeds. It is entirely possible for an sending actor on the first node to send too many messages, in this example 200 messages per second, while actor B on the receiving side can only handle 50. This is really unfortunate because we are, first of all, there is an infinite queue of messages on the actor B side. The queue becomes clogged. It's very hard to deliver new messages. We're also wasting bandwidth, which is really unfortunate. Instead, what we would ideally want is to only send 50 messages per second, which is exactly the rate actor B is able to handle. To implement that, we're doing TCP style windows. So on the receiving side, there is a window, certain amount of messages, which needs to be acknowledged as processed before any more are sent. And this is what control connection is used for. We're sending flow updates, flow window updates of the control connection to ensure that the sending side does not send more than we can handle. Finally, the actor systems in general are pretty hard to debug because they are very dynamic, but introducing network into the mix causes even more problems. So elfo provides out of the box all the metrics you need in terms of a single node. When we were developing this feature, we also made sure that elfo provides out of the box metrics for networking. So you can monitor pretty easily the state of the flow control, the state of the system actors, and everything else as well. So this ensures that engineers have complete observability, complete visibility over the system they are developing. This all, of course, in addition to the existing feature of elfo, where you can just dump all the messages in the system to a storage such as ClickHouse, and then analyze them later for debugging, for incident reporting, or something else. The interesting part is that elfo reports so much metrics, but we can actually build a mesh of services out of it. In this example, you can see that using the data, using the metrics elfo provides, we were able to build this graph of different services. Each dot here is a server running elfo. And the edges between them, each have a label of describing the number of messages, number of requests rather, sent between them. This can be, again, very useful to have a bird's eye view of your system and see where it struggles, see where if there is like a clock somewhere that you need to optimize. As a result, probably one of the most important findings for us is that we have a unified framework for distributed services. Our developers and all of our services already know how to work with message passing. By moving all of the complexity related to distributed services inside elfo, we ensure that developers, when implementing business logic, don't need to think about it. It doesn't matter for the actor whenever the receiving side is on the same node or on a completely different node. Elfo will handle the message sending and provide all the guarantees necessary. The system strives to be self-balancing through flow control, so that you don't wake up in the middle of the night because some actor decided to produce way more messages than you expected. But it also provides all the observability you need to debug your services if something awry. Thank you so much for your attention, and feel free to check out the elfo and its recent features.